Okay, everybody, welcome to today's meeting of the CUNY Online Set Theory Seminar. We're very pleased to have Eyal Kaplan, who will give us the second part of his talk, Non-Stationary Support, Iterations of Prikry Forcings and Restrictions of Ultrapower Embeddings from Generic Extensions to the Ground Model, which is joint work with Moti Gittik. Okay, Eyal, take it away.
Thank you very much. So let's start by recalling what we did last time. So we have kappa, a measurable limit of measurables. And we assume that GCH holds up to kappa. And let P kappa be the non-stationary support iteration of Prikry forcings so these forcings singularize each measurable below kappa. Let G subset of P kappa be generic over the ground model V. So let's recall some of the things we said last time. Since kappa is measurable in V, in VG, kappa is measurable as well. And moreover, every normal measure W in VG on kappa has the form U star. I'll remind this notation in a second. U star for a normal measure U in the ground model on kappa of Mitchell order 0. What is U star? Let me just. So U star is defined in VG as follows. We take interpretation of names for subsets of kappa. And for which there exists P condition in the generic extension such that JUP forces that kappa belongs to JUN, to J of the name. So every normal measure on kappa in the generic extension has the form U star for some U normal measure of order 0, which belongs to V. And actually this, if we start from this W will be of the form U star. So given W and VG as above, we can denote by U the intersection of W with V. It's not so trivial, but it belongs to V. It's a normal measure of order 0 there. We saw it last time. And this is the U for which W is U star. And now our main goal was to consider the ultrapower embedding with W. So let JW be the ultrapower embedding taken in VG to a model of the form MH, which is the collapse of ult VG with W. And we would like to consider the restriction of JW to V, from V to M. So we started speaking about it last time. We want to show how JW restriction to V can be factored to an iterated ultrapower of V. And this also helps us to understand when such an embedding is definable, to give some sufficient conditions for definability of JW restricted to V as a class of V. And the first step, we did the first step last time as well, so we can define an embedding K from MU. MU is the ultrapower of V, the ground model with U. We fix the notations, we fix all of those notations for the rest of this talk. So we have W, a normal measure on kappa and VG, when we denote by U its intersection with V. And MH is the ultrapower embedding of W. We can define an embedding K from MU to M by mapping each element of MU, which has the form JUF on kappa for some F in V, and it's mapped to JW of the same F on kappa. We just map the equivalence class of each F to modulo U to its equivalence class modulo W. And the fact that W extends U is enough for K to be elementary. So this is the first step when we want to factor JW restriction to V. It's not hard to see that JW restriction to V has the form K composed over JU, where JU is the ultrapower embedding from V to MU. Okay, so this is the first step. And in order to factor JW restriction to V completely, we're going to do a recursive process. Let's denote by kappa star the image of kappa after JU. So we have V, we have MU. At the end of the process, we will have M. So the first step is then taking an ultrapower with U, where kappa jumps to kappa star to JU of kappa. So let's keep that in mind. We will prove this today, but kappa star is actually JW of kappa. And this is the length of the iteration that I'm going to describe in a few minutes. As kappa jumps to JU of kappa, there are many measurables which are generated in MU in the interval between kappa and JU of kappa. And we're going to, we're going to take more iterated ultrapowers over MU or over the images of MU. At each step, when we take an ultrapower, we may add new measurables if we take an ultrapower with some lambda, which is a limit of measurables, a measurable limit of measurables, and this is one of the steps along the way will be to take an ultrapower with this lambda. The new measurables will be generated along this way. Eventually, all the measurables below JU of kappa, which will be JW of kappa, all those measurables should be destroyed. The question is how. If they survive in the iteration up to M, they are destroyed because we add the generic age over M, which adds an omega sequence to each one of them. But there are some measurables which are not, which do not survive all the way up to M. Another way to destroy a measurable is to take an ultrapower with a normal measure of Mitchell order on it, of Mitchell order 0 on it. Once we take an ultrapower with a measure of order 0, and the measurable is no longer measurable in the range. So this is closely related to the way JW restriction to V is factored as an iterated ultrapower. Each step in the iteration is going to have a role. There are some measurables which are going to be destroyed because we take an ultrapower along the way with them. With a normal measure of order 0, all the measures participating in the iteration are going to have Mitchell order 0. So those measurables do not survive all the way up to M, but they have a role. They're going to be elements in one of the Prikry sequences of one of the measurables added in H. So let's see more formally, let's add some more notations and describe this iteration. So we define an iteration M alpha of length kappa star. So kappa star is JU of kappa, and eventually we'll show it's JW of kappa. This is the length of the iteration. Where M0 is this MU. Let's denote by J alpha the embedding from V to M alpha, the iteration at stage up to stage alpha. So we can also say that J0 is JU. And it's going to be a normal iteration. The critical points are going to be increasing. Each time we'll take an ultrapower, it's going to be with the measure of Mitchell order 0. For alpha limit, M alpha is the direct limit of the previous steps. So it's the direct limit of the previous M betas with respect to the embeddings. J beta gamma, which is the embedding from M beta to M gamma, the part of the iteration from M beta to M gamma. This is the limit steps, and let's describe the successor steps. So assume that M alpha was defined, and let's define M alpha plus 1 plus 1. Let's denote, mu beta, beta below alpha, be the list of critical points so far. So mu beta is measurable in M beta, and M beta plus 1 is an ultrapower taken over M beta with a normal measure of order 0 on mu beta. Let's give this normal measure name U mu beta. U mu beta in M beta is the normal measure used at stage beta or after stage beta in the iteration, used over M beta. And now so this is recursive. Now let's see how mu alpha and u mu alpha are defined. So in order to understand how they should be defined, let's define a quotient embedding. Let's define an embedding, a generalization of the k alpha from m alpha all the way to m in the following way. K alpha gets an input, which is the general element, an element in m alpha, which has the form j alpha of some function f in v, applied on some of the critical points along the way. Kappa was the first critical point, so I'll always write kappa first, and then some of the mu alphas. And K alpha maps this element to JW of F on kappa mu alpha 0 up to mu alpha K. For every F in V and alpha 0 up to alpha K below alpha. So this K alpha has several properties which are not, they might be intuitive, but they're not clear or immediate. The first thing is that K alpha from M alpha to M is elementary. And JW restricted to V can be factored to K alpha composed on J alpha. J alpha is the embedding up to the model M alpha. And the second property, let's denote by mu alpha, the mu alpha, which is the critical point at stage alpha, let's denote mu alpha, let's denote the critical point of K alpha by mu alpha. Then this mu alpha is measurable in M alpha. This K alpha is defined outside of M alpha. It's defined in VG. The definition is external to M alpha, and it's not clear that the critical point of K alpha is measurable in M alpha, but it is. Property C. So mu alpha is the critical point of K alpha. We may consider the image of mu alpha under K alpha mu alpha. This is a measurable cardinal in M by B because mu alpha is measurable in M alpha, by B and A because we use the elementarity of K alpha. And we say the following thing: mu alpha appears as an element in the Prikry sequence added to its image K alpha of mu alpha in H, in the generic H. Maybe I'll say something about this. So mu alpha appears as an element in the Prikry sequence added to K alpha mu alpha. And moreover, the Prikry sequence of K alpha mu alpha is an iterated ultrapower with the, mu alpha. Take a measure on mu alpha and iterate it over M alpha omega many times. And I'll demonstrate this in a second. For instance, for the first measurable in M above kappa. So we have this property. And now we can define u mu alpha. The measure that we want to take to use at stage alpha in the iteration, u mu alpha, this is all the subset of mu alpha, such that mu alpha belongs to their image under K alpha. And we consider only subsets which belong to M alpha. U mu alpha is the measure derived from K alpha. Once we know that mu alpha is the critical point of K alpha, this makes sense to derive this measure. It's not clear that U mu alpha is a measure which belongs to M alpha, but it is. So the fourth property is that U mu alpha actually belongs to M alpha. And finally, we can say a bit more about this mu alpha. Mu alpha is the least measurable mu in M alpha, so for which two things happen simultaneously. First, it's above all the mu betas defined from so far. And second, the cofinality of mu and V is above kappa. So the mu alphas, the critical points in the iteration, are always measurables which have cofinality above kappa in V. And so those are the properties of K alpha. This is the way mu alpha is defined. This is the way the measure U mu alpha on mu alpha is defined in M alpha. And after all of those properties are proved at stage alpha in the induction, in the inductive proof, we take M alpha plus 1 to be the ultrapower embedding, to be the ultrapower of M alpha with the measure U mu alpha. So this is the construction, and we will dive into some of the details, not all of them because we don't have much time. Maybe let me just remark that after all of this is done, after this is done for every alpha less than kappa star, we have the iteration, we can define. So after all of this is done, we may consider K kappa star, the same K alpha, just for alpha equals kappa star, from the model M kappa star to the model M. And we may prove, and we will prove that this is the identity. From here, it will follow that M is M kappa star, JW restriction to V is J kappa star, and kappa star, which was the image of U under kappa, and the image of kappa under U after the first step, is actually the image of kappa under W. Kappa star originally was JU of kappa.
Could I just ask quickly? So in this recursive definition of the iteration, is it possible to tell in V what the U mu alpha is?
Yeah, so not necessarily.
Okay.
This is the question about definability of JW restriction to V, and this depends on the way we singularize in V. When we took a generic extension G, we singularized the measurables of V below kappa using measures on each of them, using Prikry forcings. This highly depends on the measures used along the way. So I'll give the complete dependence of the measures U mu alpha with respect to the measures used to singularize measurables below kappa.
I see, because that's the only thing that is not clearly definable, right? Otherwise, you can tell what the measurables are in the iteration. You just have to be able to pick the measures.
Yeah,
yeah.
The
Okay.
mu alphas are not the problem.
Yeah.
Yeah.
Right. Okay.
Okay. So I would like to demonstrate some of the things. So let me say one thing about property A. The reason that property A holds, and it's a bit technical to show it and not very interesting, but the reason that each K alpha is indeed elementary is that at each step, the measures used in the iteration, those U mu alphas, are derived from the K alphas. For instance, at stage alpha over M alpha, once we define this U mu alpha derived from K alpha, we can take M alpha plus 1 to be the ultrapower with U mu alpha and define K alpha plus 1. And the reason why K alpha plus 1 is elementary is because this U mu alpha was derived from K alpha. So it's the proof that each K alpha is elementary is just a tedious check, but this is the main point behind it. That the measure that at each step we take an ultrapower with measures derived from the quotient embeddings. I would like to concentrate on property B, and then say a few words about the other properties, not entirely prove them, and at least prove property B for the case where alpha equals 0 for the K from mu to M that we've started with. This gives some of the ideas, the main ideas in the proof for general alpha, which has one ingredient. So let me say this in a minute. So let's prove property B for the case where alpha equals 0. Namely, we have K from mu to M. We now know that K is K0. K is defined by mapping equivalence class of a function modulo U to its equivalence modulo W. And let's argue that the critical point of K is measurable in mu. Moreover, it's the first measurable above kappa in mu. After the proof, we'll see why. So I concentrate on the case where alpha equals 0 because the general case for general alpha has some technical issues that we will not have time to solve. But I think the main idea outside of these technical issues will appear. So let's see why the critical point of this K is indeed measurable in mu. So first, what can we say about it? So it's not hard to see that the critical point of this K is above kappa plus. We know that the measures U and W are normal. Kappa is mapped to itself. It's represented in both sides by the identity function, and even all the ordinals between kappa and kappa plus can be represented by the canonical functions, and kappa plus as well is represented by the successor function. So the critical point of K is above kappa plus. Let's, instead of mu0, let's just denote it by mu, omitting the sub index 0. Let's assume for contradiction that this mu is not measurable in mu. So we can now represent mu. We can take a function in V such that mu is the equivalence class of this function age modulo u. And we can take a function in VGF such that this mu is the equivalence class of f modulo w in VG. Our goal is to get a contradiction. The contradiction is going to be that mu belongs to the image of K. Mu is the critical point of K. It cannot belong to the image of K. So our goal now is to prove that mu belongs to the image of K. And this will be done by evaluating this function f. Let's see, what do I mean by that? So first, we can assume that for every xc below kappa, this f of xc is above xc plus below age of xc. Why can we assume that? So for this, we know that mu is the equivalence class of f modulo w, is strictly below its image under K. It's the critical point of K, and K maps elements, the equivalence class of age modulo u, which is this mu. It maps it to the equivalence class of the same age modulo w. So we have, for majorities of x's in the sense of w, f of xc is below age of xc, and by changing f outside of w, we can assume that f of xc is strictly below age of xc. And the fact that f of xc is above xc plus is because the critical point, this mu is above kappa plus. So we can assume that. We can also assume that this age of xc is non-measurable because mu, age represents mu modulo u, and mu is not measurable in mu, but let's still assume that it is regular. Mu is the critical point, it is regular. So let's assume this information about age. This is a statement in VG because F belongs to VG. And let P in the generic set be a condition which forces this. So we have a condition which forces this picture. Okay. We're going to apply fusion. I'll remind you what fusion is. So we assume that we have a condition P in our forcing. For every xc below kappa, let xc be a p xc plus 1 name for a dense open set with respect to the direct extension order of the forcing in the quotient forcing above xc. Then there exists P star, a direct extension of P, and a club C in kappa, such that for every C in this club, P star forces the final segment P star above Xc plus 1 into Xc. So what's the idea? We have the forcing up to stage kappa, and for every Xc, we have a dense open set with respect to direct extensions strictly above Xc. This is this Xc. So the fusion lemma says that we may take direct extension above any condition. By taking a single direct extension, we can enter many of those final segments Xc, or more precisely, many of the final segments of the direct extension enter this Xc. Many in the following sense, many in the sense that there are club many final segments. This is, I believe, the main feature of the non-stationary support. By the way, I should make this remark. I don't know if now it's the correct time, but there is a version of this work for the full support, which is almost done. And there is a version of the fusion lemma a bit more complicated, which allows some of the ideas to come through for the full support iteration. Okay, so let's apply this fusion lemma. Let's recall the situation. So given Xc below kappa, we have this edge of Xc, and we have f of Xc below edge of Xc. Let's describe now this Xc for which we want to apply fusion. Xc is going to be the set of all the conditions in the forcing above Xc, which decide the value of f of Xc up to boundedly many possibilities. We have a bounded subset of edge of Xc, such that R forces f of Xc into it. And I claim that this Xc is dense open with respect to direct extensions. After that, we will see how it helps to finish the argument to show that mu belongs to the image of K and get a contradiction. So let's see first why Xc is dense open with respect to direct extension. And here is the step where we use the fact that edge of Xc is not measurable. This was the assumption by contradiction. So let's see how. So we start from an arbitrary condition in the forcing above Xc plus 1, and our goal is to construct a direct extension R star of R, which belongs to Xc. So first, let's construct R star above edge of Xc. So we know that this f of Xc is a name in the forcing up to stage kappa. What we're going to do now is to reduce fxc to a name in the forcing up to stage edge of Xc, not including edge of Xc. We know that edge of Xc is not measurable and f of Xc is below it, and the direct extension of the forcing from edge of Xc, including edge of Xc, to the end, the direct extension is more than edge of Xc closed. Edge of Xc is not measurable, so we do not force over edge of Xc. And the direct extension is closed enough So we can direct extend R above edge of C such that R up to edge of C forces that for some alpha below this edge of C, the direct extension above edge of C reduces f of C to this alpha. Okay? This is the place where we use the fact that edge of C is not measurable. And now we reduce this f of C to a name alpha in the forcing up to edge of C. So we may consider this alpha as a name in the forcing P up to edge of C. And we're going to use another property of this forcing. I've mentioned it for a second last time. And it is that if we have a name for an ordinal in the forcing, let's say P lambda up to some lambda regular, if we have a name for an ordinal in the forcing up to P lambda, we can decide the value of alpha, or more precisely guess the value of alpha up to less than lambda many possibilities by taking a single direct extension. Maybe let me state it formally. Another property of the forcing, given a P lambda in the iteration up to stage lambda for some lambda regular, given a P lambda name alpha for an ordinal and a condition P in the forcing up to lambda, there exists a set of ordinals A of cardinality less than lambda and a direct extension of P such that this direct extension forces that alpha belongs to A. So if we have a name for an ordinal, we can decide its value up to less than lambda many possibilities. Now this ordinal is below edge of C, and it's a name in the forcing up to edge of C. So there exists R star restriction edge of C, a direct extension of R up to edge of C, and a bounded subset of edge of C. Since this alpha is below edge of C, we're guessing it up to edge of C many possibilities. The set of guesses is bounded in edge of C. So this R star forces alpha into A. So together, R star forces that f of C, which is this alpha is forced by the upper part of R star above edge of C, belongs to this set A. And thus this R star belongs to E of C. Okay, this is the proof that E of C is dense open with respect to direct extensions. How can we use that proof to finish our argument? So let's just recall the situation. We had mu, the critical point of K. Mu is represented by this H modulo U, and it's represented by this F modulo W. And our goal is to prove that this mu belongs to the image of K. This is the way we get a contradiction. So we had P in G, which forces that f of C is below edge of C for every C, below kappa. And now by fusion, there exists P star direct extension of P. We can do this as high as we want above P. So let's assume that we did a density argument and we have P star already in G. There exists P star in G and the club C in kappa, such that for every C in C, P star up to Xc plus 1 forces P star above Xc plus 1 into XC, or more precisely, what does it mean to be in XC? This means that there exists a bounded subset A of H of Xc, such that P star above Xc plus 1 forces F of Xc into this A. And since this A now depends on Xc, let's call it A of Xc, for every Xc separately. This A of Xc is the name in the forcing up to Xc plus 1. Let's define A star of Xc completely in V. For every C in this club C, let A star of Xc be the set of ordinals below H of Xc, such that some extension of this condition, for some Q, not necessarily direct, some extension of this condition forces that this gamma belongs to A of Xc. So look, so we have this A star of C defined completely inside V, and I claim that A star of C is a bounded subset of H of C. So we know that we have GCH. So the cardinality of the forcing up to stage Xc plus 1, including Xc, if Xc is measurable, is at most Xc plus. Last time, I believe I didn't emphasize the use of GCH, so this is one of the places where we use GCH. So this A star of C is still bounded in H of C. We know that H of C is strictly above this Xc plus. We have a name for a bounded subset A of C of H of C. And we ask what are the possibilities of elements in this set, and we cannot have H of C many possibilities for element in this set. Otherwise, we could stabilize single Q, which forces H of C of them into this set, contradicting the fact that A of C is bounded in H of C. So the fact that this forcing has cardinality strictly below H of C implies that A star of C is still bounded inside H of C. Okay? And for every Xc in C, we know that P star, what do we know about P star? We know that P star says that F of C belongs to this A of C, which is contained in A star of C. A star of C is the set of possibilities for element in A of C. So P star forces that F of C belongs to A star of C. And this is true for every C in a club, which is a set in U. And thus is a set in W. So JW of this P star forces that the equivalence class of this F modulo W belongs to the equivalence class of the function. Each Xc is mapped to A star of Xc. This is a function in V. For every, it's defined for every Xc in C, which is a set in W. Its equivalence class modulo W contains the equivalence class of F modulo W as an element. But what do we know? We know that P star was in G. So JWP star belongs to H. H is the image JW of G. Right? P star is in G, so JWP star belongs to JW of G, which is this H. So in MH, we know that the equivalence class of F modulo W, which is what we denoted, F was the function which represents mu. It belongs to this set. And what is this set? So it's JW of the function. We apply JW on the function which maps each Xi to A star of Xi on kappa. But we made a lot of effort to give here a function from V, because we can express it as K applied on JU of this function on kappa. This is how K is defined. K maps elements J of the form JU of F on kappa. It maps them to JW of F on kappa. So by the way K is defined, and since this function actually belongs to V, we get this. We get K of this set. And what can we say about this set? We know that each A star of Xi is a bounded subset of H of Xi. So the equivalence class of A star of Xi modulo U is bounded. This element is a bounded subset of the equivalence class of H modulo U, which is this mu. So we have here a bounded subset of mu, and mu is the critical point of K. And when we apply K on a bounded subset of the critical point, this is a subset of the image of K. So eventually this mu belongs to the image of K. Or even we can derive the contradiction in another way. Those are elements below mu and boundedly many, less than mu many. So K on these elements is just the elements themselves, and mu cannot be one of them. They are all below mu. In any one of those two ways, and we get a contradiction. Okay. So, okay, I hope it wasn't too tedious. This is the proof that the critical point of K alpha, okay, K0, because we proved it only for alpha equals 0, the critical point of K0 is measurable in M0. How is the general proof different? In general, this mu alpha, how did we prove? How did we start the proof? We represented this mu alpha modulo mu, which is the first stage in the iteration, and modulo w, modulo u and modulo w. Now, in the general case, when we want to prove that mu alpha for alpha which is not 0 is measurable in M alpha, this part is different. We represent mu alpha in M alpha, and the representation may use some of the critical points below mu alpha. The representation is of the form J alpha of a function H applied on kappa and some of the previous mu alphas. And we need to take care to consider those mu alphas inside the argument. More precisely, we need to generalize the fusion lemma so we can apply it to a function which depends on several variables. This is the function which replaces H in the argument above. And the main idea is to sort of apply fusion for each one of these variables separately. This is done by a generalization of the fusion lemma, which is quite technical. And this is the part, this is the ingredient of the proof which I omitted for the case where alpha equals 0. I didn't omit it. It's not necessary for the case where alpha equals 0. And since it is a bit technical, it's going to take some time to show it. And I'll not show it, but I hope that the main idea, came through. Okay. So maybe in the time I have left, let me talk a bit. I want to show two main things, which is what is the connection between those measures U mu alpha used at stage alpha in the iteration over M alpha. I want to show what is the connection between them and the measures used below kappa for singularizing, enforcing P kappa for singularizing measurables below kappa. So I want to say a few words about this connection. This will lead us to a discussion about the definability of JW restriction to V. And after that, I want to show the argument that K kappa star is indeed the identity. So several things about the measures U mu alpha. By the way, you can see that in the proof, at least of property B, that the critical point of K alpha is measurable in M alpha. It was not specifically crucial that the forcing is an iteration of Prikry forcings. We just used properties of the direct extension order. We didn't use the fact that the forcing, the forcing, I don't know, stage age, okay, at age of C we didn't force, but we didn't use the fact that the forcings are more specific Prikry forcings. So let's see how the fact that we use Prikry forcings below kappa in VG, let's see how this determines what is the value of the measures U mu alpha. So for every C below kappa measurable, we use or we apply Prikry forcing, the Prikry forcing in the generic extension up after the C first steps. Let U star C be the pixie name for the measure used in this Prikry forcing. This is a name for a measure, a name which depends on the first C steps in the iteration. And note that as we had at kappa itself, every measure on Xi in the generic extension after Xi many steps has the form U star Xi for some U Xi, which is its intersection with V. So every measure comes from V, extends the measure from V, even along the way. Let U Xi be just the name of the intersection of U star Xi with V. And every condition forces that this U Xi belongs to V. It just don't know which one of the measures on Xi in V it is, but every condition knows that this U Xi belongs to V by what we proved. So we may take a name U for the sequence of, let's U be the sequence of names. And in VG, we can also define, let's call it U vector. In VG, we can also define the interpretation of those names. So we're interested in the intersection of the measure used at stage C in the iteration with V. Those are the measures which we're interested about. And this U is not necessarily in V. But U is a sequence of elements of V, of measures in V. It's just that V doesn't know about the entire sequence. The entire sequence belongs to VG. And so we can say the following thing, only say we will not have time to prove this. We can apply in VG JW on this U. JW of this mu is a sequence of measures. Let's look at the measured place K alpha mu alpha for some alpha below kappa star, for some alpha along the way. K alpha of mu alpha. The measure in this place is K alpha of U mu alpha. U mu alpha, I didn't show the argument, but U mu alpha belongs to M alpha. We can apply K alpha on it, and K alpha maps mu alpha, U mu alpha, to a measure in the sequence JW of U. Which measure? The measure on the measurable K alpha of mu alpha. So intuitively, so first of all, this gives the connection between the measures U mu alpha and U. And one thing before I forget to mention this, if somehow this U belongs to V, we can arrange situations where this U belongs to V. For instance, when we define the iteration P kappa, just say in advance, once we define this P kappa, use canonical names. Stage for every C below kappa, use the canonical name of UC. Say in advance what is the measure UC we want to use to singularize C. So this might happen that U belongs to V, and also it happens quite a lot in applications of this forcing. If U belongs to V, then what the above equality shows, it shows that U mu alpha is J alpha of this sequence U applied on mu alpha by elementarity of K alpha, right? If we omit K alpha from here, and we know that JW is K alpha applied on J alpha, we are left with J alpha U on mu alpha. We omit this K alpha as well. In particular, in this case, JW restriction to V is definable in V. Because the measures used along the way are definable in V. So let me demonstrate this point. So we have the iteration. Last time we talked about the first omega many steps in the iteration. And the first omega many steps result in a model M omega. And after them, there are the rest of the steps in the iteration. So we have kappa, which is mapped to JU of kappa, this kappa star. And now in M0, we have mu0, the critical point of K0. We know that it's measurable in M0. Let's note that it's the first measurable above kappa in M0. Why is it the first measurable above kappa in M0? If there were measurables in this interval, so let me write it in M0, mu0 is measurable, we know, but I argue now more, is the first measurable above kappa. Why? If lambda between kappa and mu0 was measurable in M alpha, if we had such lambda measurable in M alpha, then what do we know? We know that this lambda stays in place for the rest of the iteration. The rest of the iteration fixes lambda because the critical points, the first critical point is mu0, and the next critical points are going to be above this mu0. All of them are going to fix this lambda in place. This means that lambda is measurable in M. K, the rest of the iteration from M0 to M, fixes lambda in place. So lambda is measurable in M. And thus, if lambda is measurable in M, we have the generic extension in MH. Lambda is one of the measurables for which we add a Prikry sequence. So the cofinality of lambda is omega. And thus, this is true as well in VG. The cofinality of lambda is omega. This Prikry sequence, which belongs to MH, belongs to VG as well. So, in V, the cofinality of lambda cannot be above kappa. Our forcing, if the cofinality of lambda in V was kappa or higher, our forcing would preserve it. It preserves things above kappa, cofinalities above kappa. But what do we know? We know that lambda is measurable in M0. M0, if lambda is measurable in M0, it's regular in M0. M0 is just the ultrapower of V with U. If lambda is regular in M0, then the cofinality of lambda in V is above kappa. So this is a contradiction. Or maybe let me say it like this. If in lambda, the cofinality of lambda is below kappa, then the sequence witnessing this belongs to M0 as well, showing that lambda is singular in M0. So we know that mu0 is the first measurable above kappa in M0. And now, after the first step in the iteration, mu0 is mapped to mu1. And the similar argument shows that mu1 is the first measurable above kappa in M1. How is it mapped to u1? We take an ultrapower with the measure u mu0, the measure derived from K. Now over M1, we take an ultrapower with the measure u mu1. Note that that u mu1, the measure taken on mu1, is the image of u mu0. Why is that? Because we can apply, this is true because we can apply, let's apply K1 on both sides. We have K1 of u mu1, and we have K1 on J01 of u mu0. K1 on J01, if we have M0 and we have M and we have M1 in the middle, K1 is the embedding from M1 to M, J01 is this embedding, and when we use the composition of K1 with J01, this is just K0 on u mu0. And what do we know? We know that both sides are the same. Why? Because this is JW of the sequence U applied on K1 of mu1, and this is JW of the sequence U applied on K0 on mu0. And K1 of mu1 and K0 of mu0 are the same. K1 of mu1 is the destination of mu1 after omega many steps in the iteration, actually. let's say it like this, it's after omega many steps, but let's say it after all the steps up to m, and k0 of mu0 is the destination of mu0 after those steps, and this goes in line, this goes through mu1, it's the same destination. So those are the same, and thus those are the same, and thus those are the same. So I only say this only to show that the measure used over m1, u mu1, is the image of the measure u mu0. And this continues. We take iterated ultrapower, omega many steps with the images of u mu0. This results in mu2, mu(n) for every n less than omega, up to the supremum of the mu(n)s. This is not mu omega. Mu omega is the first measurable above the supremum with cofinality above kappa, if you remember property E. We required that the cofinality of the mu's are, the cofinalities of the mu's are above kappa. So mu omega cannot be the supremum, and the next step after m omega is going to be to take an ultrapower with this mu omega strictly above the supremum. This means that the supremum is fixed until the end, until m. It stays in place. It's a measurable in m, and the Prikry sequence added to the supremum in m is more or less the sequence mu0, mu1, mu(n) for every n less than omega. I say more or less because the non-stationary support allows a bounded initial segment below mu0. So this is actually a final segment of this Prikry sequence. And every Prikry sequence, every measurable in M above kappa has a Prikry sequence which has this form. It's an iterated ultrapower using a single measure and its images over some M alpha. Here it started from M0, but we might, after, for instance, stage omega, after M omega, we're using mu omega, u mu omega and its images to generate a Prikry sequence for the second measurable above kappa in M, and so on. So this is how Prikry sequences added in age above kappa look like. And the final thing, which I think will take 5 minutes, is to show that this process indeed ends after kappa star many steps, namely that k kappa star is the identity function. But before that, if there are any questions about this picture, okay. So let's argue, and this is a quick argument, k kappa star is the identity function. So we have this kappa star, or maybe before it, we have those mu, let's call how k kappa star is defined. K kappa star applied on an element of the form j kappa star of f on the sequence of critical points, finitely many of the critical points so far. This is mapped to jw of the same function f on the same sequence. So from this definition, it's not hard to see that the critical point of k kappa star, it actually doesn't exist, this critical point. But let me phrase it like this: it's at least the supremum of the mu alphas for alphas below kappa star, because k kappa star maps each such mu alpha to itself. And it's not hard to show that even ordinals, if we have an ordinal below some mu alpha, it's mapped to itself as well. The critical point is greater or equal than the supremum of the mu alphas. So note that the mu alphas below kappa star have supermum mu kappa have supermum kappa star. We have this kappa star, which is the image of kappa. Once we take this ultra power, we have here in the interval kappa star many measurables. And as we take more and more ultra powers, we have more measurables in this interval, but overall the number of measurables remains kappa star. And when we do this iteration kappa star many times up to kappa star, those mu alphas that are unbounded in kappa star. We will go through all the measurables. We'll go through all the measurables in the interval, and even in this interval between kappa and kappa star, and even more measurables, because more measurables may be generated along the way. So the supermum is kappa star. Now let us argue that every ordinal eta belongs to the image of K kappa star. This is enough to show that K kappa star is the identity. So we're going to use similar ideas. The main idea behind here is fusion, and the fact that if we have a name for an ordinal, we can decide it by less than kappa many possibilities. Let's see how. So let f in Vg be a function such that eta is the equivalence class of f modulo w. So we argue that there exists f in V and a club C in kappa, such that for every C in C, small f of C belongs to f of C, and the cardinality of f of C is below kappa. I'll show in a moment why this is true. This is an application of the fusion lemma, a similar application to what we've seen before. But why this finishes the proof? Before we'll prove the claim, why this is enough? It's enough because then this club C belongs to U, and thus it belongs to W, and thus in M age, in the ultra power by W, we have that the equivalence class of F modulo W belongs to the equivalence class of large F modulo W. But this large F comes from V. This is like K kappa star. This is, maybe let me, this is JW of this F on kappa, and JW can be composed to the form K kappa star on J kappa star. So we may apply K kappa star on J kappa star of the same F function large F on kappa. And we know that the cardinality of F of C is below kappa for every C. So the cardinality of J kappa star of F on kappa is below J kappa star. So the cardinality of this set is below J kappa star of kappa, which is kappa star. So this kappa star, it remains in place after kappa star many steps, taking iterated ultra power with measurables below kappa star. This kappa star remains in place. It's measurable in MU, and it remains measurable in each step in the ultra power, and cannot move by taking an ultra power below it. So J kappa star of kappa is kappa star. This is the critical, this is less or equal to the critical point of K kappa star. So overall, we have K kappa star applied on something of cardinality less or equal than its, not less or equal, strictly less than its critical point. So this is a subset of the image of K kappa star. So this eta that we've started with belongs to the image of K kappa star. And why is the claim true? So the claim follows by fusion. we can define XC, the set of conditions in the forcing above C, such that for some A, a set of ordinals of cardinality less than kappa, these are forces f of C inside A. We know that f of C is the name in the forcing up to stage kappa. And we know that by taking a single direct extension in the entire forcing, but even in the interval above C, by taking a direct extension, we can guess the value of f of C but up to less than kappa many possibilities by taking a single direct extension. So this XC is dense open with respect to direct extensions. And we can apply fusion with respect to this XC and find by fusion there is P in G such that P in G and the club C in kappa such that for every C in C, P restriction C plus 1 forces P above C plus 1 into XC, or in other words, P restriction C plus 1 forces that there exists a set A of C with cardinality less than kappa, such that P above C plus 1 forces that f of C belongs to this A of C. This is very similar to what we did before. But this A of C is the name in the forcing after C steps in the forcing peak C plus 1. So we can just define f of C to be the set of all possible values of elements of A of C. Possible values as witnessed by some extension of P restriction C plus 1. So we take all the gammas such that some Q forces into the set A of C. And since this part of the forcing peak C plus 1 has cardinality less than kappa, then this f of C has cardinality less than kappa. So the cardinality of f of C is still below kappa, and for every C in C, P forces that f of C belongs to f of C, as we wanted. Okay, so this finishes the argument. There were some more things that I wanted to say, but I think they will take, I'm not sure we have more time. I think they will take time. So I think this will be a good point to stop, unless you have questions.
All right, thank you very much. Great talk, really. I enjoyed it a lot. Let's see. I don't think I have any questions. I found it very clear, the whole presentation. Very, very nice. I mean, also the fact that you know, how you omitted some technical details, I think was a good choice. I think you get a good idea of how it works. Are there any questions from other people? Doesn't seem so. It's very quiet. Okay. Well, okay. I'll just say thank you again for the great talk. And yeah, have a good night.
Thank you very much. Thank you for listening.
Yes,
Okay.
thank you.
Yeah, it was great.
Okay.
Have a good night.
All right. Bye-bye, everybody.
Bye.